Across the entire sky, a faint glow of ancient radiation is pressing against the most sensitive instruments ever built. Cosmologists analyzing data from ESA's Planck mission are detecting microscopic temperature fluctuations embedded within this signal, variations measured to a precision of 1 part in 100,000. This fossil light, the cosmic microwave background, is the oldest observable radiation in existence, carrying encoded within it the complete structural blueprint of everything that would ever form. To understand why this light is rewriting our models of cosmic origin, we first have to understand what the universe looked like 380,000 years after it was born. Right now, every single direction you look north, south, east, west, straight up through your ceiling, ancient light is passing through your body. You cannot feel it, you cannot see it, but it is there and it has been traveling toward you for 13.8 billion years. That light has a name. Scientists call it the cosmic microwave background, or the CMB. You can think of it as the universe's baby photo, the oldest snapshot of reality that physically exists. Not a simulation, not a theory, an actual measurable signal that fills every corner of space, in every direction, equally. And when scientists finally learned how to read it clearly, what they found inside it was deeply unsettling. If you are finding this kind of content genuinely fascinating, subscribe to Space Aquarius. What the universe looked like before this light existed? To understand why the CMB matters so much, you have to go back to a time when light itself could not move freely. In the first moments after the Big Bang, the universe was not dark and empty the way it is today. It was a dense, superheated plasma, a churning soup of particles so hot and so tightly packed that light could not travel in a straight line. Every time a photon, which is just a particle of light, tried to move forward, it immediately collided with a free electron and got knocked sideways. Think of it like trying to walk through a packed stadium at halftime. You are not getting anywhere fast. This went on for roughly 380,000 years. The universe was completely opaque, sealed shut, no light escaped, no signal traveled. It was, in every practical sense, a wall. Then something changed. The universe had been expanding since the moment of the Big Bang, and as it expanded, it cooled. Slowly, steadily, the temperature dropped to around 3,000 degrees Celsius, 5,432 degrees Fahrenheit, still extraordinarily hot by any human standard, but cool enough for a critical transition to occur. Electrons, which had been flying freely through the plasma, began to slow down enough to be captured by protons. Together, they formed the first neutral hydrogen atoms. This moment has a name. Scientists call it recombination. And the instant it happened, the universe changed completely. With the free electrons now locked inside atoms, there was nothing left to block the light. The cosmic fog lifted. For the first time in 380,000 years, photons could travel freely across space, every direction, simultaneously, carrying with them a perfect record of what the universe looked like at that exact moment. That is the light we are detecting today. That is the CMB. What scientists are actually seeing inside it. Here's where it gets interesting and where the tension starts to build. When ESA's Planck satellite mapped the CMB in extraordinary detail, scientists expected to find something relatively smooth, a uniform glow with only the faintest variations in temperature from one patch of sky to another. And broadly, that is what they found. The CMB is remarkably consistent across the entire sky, but not perfectly consistent. Embedded within that ancient light are tiny temperature fluctuations, variations of just 1 part in 100,000. That sounds almost too small to matter. It is not. Those microscopic differences in temperature represent differences in density from the early universe. Regions that were ever so slightly denser than average. Regions where matter was just barely more concentrated. You can think of it like this. Imagine you are looking at the surface of a calm lake. From a distance, it looks completely flat. But up close, you can see tiny ripples. Those ripples are not random. They were caused by something specific. A stone dropped, a wind gust, a disturbance. The CMB ripples work the same way. They are the imprint of quantum fluctuations from the very first fraction of a second after the Big Bang, stretched across the entire observable universe by a period of explosive expansion called inflation. Those ripples became everything. The slightly denser regions pulled in more matter through gravity. Over hundreds of millions of years, those regions collapsed into the first stars, the first galaxies, the first black holes. The large-scale structure of the universe, every galaxy cluster, every cosmic filament you have ever seen in a deep space image, traces directly back to those tiny temperature variations in the CMB. The universe's entire architecture was written into that ancient light before a single star ever formed. The part that should make you uncomfortable. Here is the open question that keeps cosmologists awake at night. The CMB is almost perfectly uniform across the entire sky. And that is a problem, a serious one. Think about what that means physically. The light reaching us from one edge of the observable universe and the light reaching us from the exact opposite edge, those two regions of space are so far apart that under normal physics they could never have been in contact with each other. The universe has not existed long enough for light to travel between them. They should have no reason to be the same temperature. But they are, to within a tiny fraction of a degree. How does that happen? How do two regions of space that have never interacted end up at the same temperature as if they agreed on it? This is called the horizon problem. And the leading explanation, cosmic inflation, proposes that in the first unimaginably brief moment after the Big Bang, the universe expanded faster than the speed of light. Not matter moving through space, but space itself stretching. In a fraction of a second shorter than any unit of time you have ever heard of, the universe grew by a factor of 10 to the power of 26. That is a 1 followed by 26 zeros. Before that expansion happened, those distant regions were in contact. They were close enough to reach thermal equilibrium. Then inflation stretched them to opposite ends of the observable universe, locking in that uniform temperature like a photograph. The CMB is the evidence that this happened. Those tiny ripples, the ones that became every galaxy, are the quantum fluctuations that inflation magnified from subatomic scales to cosmic ones. Scientists at the Center for Astrophysics at Harvard and Smithsonian are operating instruments like BICEP 3 at the South Pole, specifically to search for the fingerprint of inflation inside the CMB. The South Pole is used because the extreme cold and dry air there makes it one of the only places on Earth where these faint signals can be detected without interference from atmospheric water vapor. They are looking for a specific pattern in the CMB called B-mode polarization, a subtle twisting in the ancient light that would be the direct signature of gravitational waves produced during inflation. Waves generated when the universe was a fraction of a second old. They have not found it yet. But the search is ongoing. What happens if we find it or if we do not? If BICEP 3 or a future instrument detects that B-mode signal, it would be the most significant confirmation in the history of cosmology. Direct physical evidence that inflation happened. Direct evidence that the quantum world and the gravitational world were unified in the first instant of existence. And if they never find it, if the signal is simply not there, then the leading theory for why the CMB looks the way it does falls apart. And scientists would have to go back to the beginning. Literally, some researchers at Harvard's Institute for Theory and Computation are already working on alternative models. One possibility is that the Big Bang was not a beginning at all, but bounced the collapse of a previous universe, triggering the expansion of this one. A big crunch becoming a Big Bang. The CMB would look different under that model. Subtly, measurably different. The data from Planck and BICEP 3 may already contain the answer. Scientists are still reading it. That ancient light passing through your body right now, it knows what happened. The question is whether we are smart enough to ask it the right questions. So when you step back and look at all of this, the oldest light in the universe is not just a relic, it is an active instruction manual for how reality assembled itself, and we are only beginning to decode it. Every answer the CMB gives us opens 3 more questions we did not know to ask. Current data suggests that within the next decade of observation, BICEP 3 and its successors will either confirm inflation or force cosmology to rebuild from the ground up entirely. Have you ever stepped outside on a clear night and genuinely felt the scale of what is above you? Does knowing that ancient light is physically passing through you right now change how that feels? Drop your answer in the comments below. If this one made you think, send it to someone in your life who still believes science has most of the big answers figured out. Subscribe to Space Aquarius, where the universe finally makes sense,